Okay, chapter 15, amines and amines. Let's get started. Amines are derivatives of ammonia. By now you should know what ammonia is. So the formula for ammonia is NH3. You would have seen that in general chemistry. You also would have learned the molecular geometry of ammonia. It looks like this, and we call this the trigonal pyramidal geometry. These bond angles between these bonds are a little less than 109.5 degrees. So that's a review from Chem 101. The most important type of organic base that are found in nature, so amines are bases. They're not strong bases like sodium hydroxide or potassium hydroxide, but they are weak bases, and they are bases nonetheless, organic bases. And if we consider them like a substituted ammonia, the R group that we have shown here, or these two, or these three, those R groups could either be aliphatic or aromatic. And so if we have one R group on our amine, we call that a primary amine. If we have two R groups, we call it a secondary amine. And if we have three R groups on a nitrogen, we call that a tertiary amine. If we compare the trigonal pyramidal structure of ammonia versus a tertiary amine, that's what's being shown down here because we have three R groups, so more accurately, we can call that a tertiary amine. These structures try to show the three-dimensional structure of ammonia and the tertiary amine, but I always think it's better to draw the lone pair, like this, maybe in the orbital like this, in the plane, and then have one hydrogen going in back of the page like this and have the other one coming out in front like that. And that really shows us that not only does it have the trigonal structure, but it's pyramidal, right? It's a pyramid. And the same thing applies to the tertiary amine. Again, we have the nitrogen, we have the lone pair like this, we have R, and then we have the other R groups. One of them is in the back like this, and then one of them is coming out in front like that. And, in order to get to the tertiary or the trigonal pyramidal structure, you've got to understand the tetrahedron, right? The tetrahedron. And if I just stop broadcasting here for a second and I show you the tetrahedron, this is a shape that you would have learned in general chemistry, and we also talked about it when we discussed alkanes. So here's the tetrahedral shape. If I rip off one of those atoms and I say, okay, well, this black sphere here, this is a nitrogen, here are my three hydrogens, and here's my lone pair. You can see how it is trigonal, right? It's a triangle, those three atoms, but it's also a pyramid. It's not flat, right? You can see how there's a pyramid shape there. So that's where the trigonal pyramid comes from. All right. And so the take-home message is that you have to understand that amines have that trigonal pyramidal structure or molecular geometry. All right, classification of amines. I've already covered this, but we'll go over it again. If we have three hydrogens attached directly to our nitrogen, that is simply ammonia, right? NH3, right? Everybody should know what ammonia is by now. If I have one R group, it's a primary amine. Two R groups, it's a secondary amine. And three R groups, of course, make a tertiary amine. These molecules shown down here, methylamine, dimethylamine, and trimethylamine, these are just examples. Okay, so if the R groups were all methyl groups and I had only one methyl group, right, that would be methylamine. And again, I'll show you where these other names come from. If we have two methyl groups on the nitrogen, then it would be dimethylamine. And if we have three, it's trimethylamine, like that. So primary, secondary, and tertiary amines. The physical properties of amines, it says here that amines form hydrogen bonds, but not as strongly as alcohols. And you'll probably remember that the requirement for hydrogen bonding is that you either have a bond between oxygen and hydrogen, like this, between nitrogen and hydrogen. And I'm just, boxing in to show the oxygen, hydrogen, and nitrogen hydrogen bonds, or a bond between fluorine and hydrogen. Now, the reason why we have hydrogen bonding in amine is obvious. It's because we have nitrogen-hydrogen bonds in primary and secondary amines. The reason why the hydrogen bond between amines that are shown, down here and right here, the reason they're not as strong as those between alcohols is because the electronegativity of nitrogen is less than the electronegativity of oxygen. And so the net result is that you'll see that you have more partial negative charge on the oxygen of an alcohol than you do, you know, in amine, right? Oops, I should have put delta minus there. Yep, fix that. All right, so again, it's just based on electronegativity. Now here's an example of primary amines. So all of the amines shown in this example down here, they're all primary amines. You can see all the delta pluses and delta minuses are written in, and we have a couple of hydrogen bonds represented here and here, like that. Now, if you're wondering, could I throw another molecule of, of that amine in there? Absolutely, you could. You could draw more hydrogen bonds. Okay. It also says that tertiary amines cannot hydrogen bond. Well, that hopefully makes sense to you, because if I have a tertiary amine, right, I have only R groups attached to my nitrogen. I don't have any hydrogen, so I have no nitrogen-hydrogen bonds in a tertiary amine. So we cannot have hydrogen bonding between two tertiary amines. What about the boiling points of amines? We've talked about boiling points of lots of different compounds in this class. And we talked about intermolecular forces like London forces, dipole forces, and hydrogen bonding. But where do the amines stack up? Well, if we look at this slide here, it tells us that the amines have boiling points somewhere between that of an alkane and an alcohol. So if we look at propane, ethanamine, and ethanol, which all have molar masses that are pretty close, from 44 to 46 grams per mole, you can see that we get a wide variety, or quite a range of boiling points, right? We go from minus 42 for propane all the way up to 70, almost 80 degrees for ethanol. And then ethanamine is somewhere, kind of in the middle. It's around 20 degrees, 16.6 degrees. And why would that be? The only intermolecular forces that are experienced by propane are London forces, right? The weakest of all the forces. Ethanol, it has London forces, it has dipole forces, but it also has hydrogen bonding, which is the strongest of all the intermolecular forces. Now, ethanamine does have nitrogen-hydrogen bonds. And so it does have hydrogen bonding, but what did we say last slide? We said that the hydrogen bonding between amines is weaker than that between alcohols, and so the net effect is that it's going to take less energy to take molecules of an amine, like ethanamine, in the liquid phase and get them to separate or to vaporize or to be converted into gas, okay? So that's where amines stack up between alkanes and alcohols. What about a comparison between primary, secondary, and tertiary amines? Well, it says here the tertiary amines boil at a lower temperature than primary or secondary amines of a similar molecular weight. Look at all three of these amines that are shown on the bottom. You got propylamine, ethylmethylamine, and trimethylamine. I'm reading the names that are in the brackets, and of course we'll get into nomenclature in a little bit. But if you look at the molecular weights or the molar masses of all three of these amines, they're all identical. Okay, they all have this exact same molecular formula, but there's a variation in their boiling points, right? We go from 48.7 for the primary amine, we go to 36.7 for the secondary amine, and then we drop all the way down to 3 degrees or 2.9 for the tertiary amine. Well, hopefully you're connecting the dots by now and noticing that a tertiary amine, again, doesn't have hydrogen bonding, right? The tertiary amine is only going to have London forces, and dipole forces. Dipole forces, okay? Whereas these two compounds here are going to have both of those forces. Right, they're going to have both of those forces, and they're going to have hydrogen bonding. Okay, and that is why they're going to have higher boiling points. Now, the reason why the primary amine, propylamine, has a little bit higher boiling point of around 12 degrees Celsius, higher than the secondary amine, is because here we only have, in ethylmethylamine, we only have one opportunity for hydrogen bonding, whereas in propylamine, we have two opportunities, right? We have two nitrogen-hydrogen bonds, okay? Give me a thumbs up if you just follow me thus far on physical properties and the structure and molecular geometries of amines. Good, I'll take that. Yep, okay, good. Awesome, excellent. Well, let's keep going, and we're gonna get into another comparison of mean boiling points. If we compare the boiling points of, let's see, what do we want to compare here? If we compare the boiling points, let's start with these three right here. Okay, these three at the bottom: ethanamine, propanamine, butanamine. Again, we're going to get into the nomenclature later, but what do you see? What's the difference between these three molecules? They're all primary amines. The only difference is the length of the carbon chain, right? We have 2 carbons in ethanamine, we have 3 carbons in propanamine, and we have 4 carbons in butanamine. Now, what's the effect in boiling point? It gets higher and higher and higher. They all have the same capability of hydrogen bonding, right? They all have 2 nitrogen-hydrogen bonds. What's the difference between them? Is that as the length of the hydrocarbon chain increases, we have increased London forces, and therefore it's just based off of molar mass, right? And chain length, I guess, is the chain gets longer and longer. We have increased London forces between those nonpolar chains, and therefore the boiling point is going to be increased. Let's look at one more trend on this, which is this trend here from methanamine or methylamine to dimethylamine to triethylamine. And we already looked at these molecules, and methylamine is a primary amine, dimethylamine is secondary, and then trimethylamine is tertiary. Now these molecules differ in molar mass, so we can't draw a correlation between molar mass necessarily with boiling point, but we can see a trend, and that's that as we go from the primary to the secondary, the boiling point increases. They both have hydrogen bonding, but the reason this one, the dimethylamine, is going to have a higher boiling point is because of the increase in molar mass by adding that second methyl group. Now, this is the trend I really want to look at before we leave the slide, and that's going from dimethylamine to trimethylamine. You notice that the molar mass is increasing, right? Because we're adding a third methyl group. But what happens to the boiling point? It actually drops. Could anybody answer me as to why, even though the molar mass is increasing? Thanks, Greg. You get it before I could even get it out of my mouth. Greg says there's no hydrogen bond in trimethylamine. All right, there we go. Johnny, I would say there's no reason, no good answer for your question, except to say there's a reason we call them common names, okay? Because common names are more commonly used than IUPAC names. That would be my best answer to that. In fact, most compounds that we have common names for, if you were to ask a chemist, you know, to hand you something and give them the IUPAC name, they usually have to think about it pretty hard because common names are quite commonly used. Here's another comparison. You know, these are real classics in Chemistry 102, where we love to compare the boiling points with different functional groups. There's kind of the same trend shown 3 times on one slide, but if we go from methanol, which is CH3OH, and then if we compare that to methylamine or methanamine, which is CH3NH2, you can see they have similar molar masses, but what happens? The boiling point drops dramatically as we go from methanol to methanamine. And the reason why is just the strength of the hydrogen bond, right? The hydrogen bond in an alcohol is stronger than that in an amine. We see the same trend with ethanol and ethanamine. We see the boiling point drop, and we see the same thing with propanol and propanamine. Okay, so these are just analogous alcohols and their analogous primary amines. Nothing more than that on that slide, but still interesting nonetheless. Let's take a look at some examples here and see if we can come up with some answers. And this is a question, you know, it would make a great multiple choice question, or so there's actually a series of questions on here. Which molecule in each pair? We've got 1, 2, 3, and 4. Okay, we'll call those the numbers. Which molecule in each pair will have a higher boiling point? So let's start with the first one, methanol or methylamine. Well, hopefully by now you've gotten the feeling for a little bit of the nomenclature that methanol is this alcohol and methylamine is simply a methyl group with an NH2. Who could tell me which one of these should have a higher boiling point? And we've already looked at these on a previous slide. Absolutely, Greg. The answer is methanol. Why? Because it has stronger hydrogen bonding than methylamine does. Yeah, great. The next one is dimethylamine, rather. Dimethylamine, which would be this CH3NH and then another CH3. or water? What about this one? Yeah, water, absolutely. Water's got a much higher boiling point. Right? Water's got a boiling point of 100 degrees. And that's because it's got two oxygen hydrogen bonds for hydrogen bonding. And again, the hydrogen bond in water is much stronger than that in an amine. The next one is based on molar mass. We've got methylamine, which would be CH3 NH2, which I'm sure you picked up on the first one, and ethylamine, which would be CH3 CH2 NH2. Which one of these would have a higher boiling point? Not a trick question. Yeah, ethylamine, and it's because of a longer carbon chain. Nothing more than that. Nothing more than that. So we'll highlight that. And then the last one, I'll do it for you, is propylamine, which is an amine, versus butane, which is an alkane. Well, wow. If we draw the structure of propylamine, it's CH3, CH2, CH2, primary amine, and butane, which is 1, 2, 3, 4. Well, butane is simply an alkane. Right? The only intermolecular forces experienced by alkanes are London forces. And so the amine, propylamine, since it has hydrogen bonding, and they both have similar molar mass, it's going to have a significantly higher boiling point. So there we go. We're already able to look at some molecules and come up with some trends with respect to boiling points. Let's talk a little more about physical properties and discuss solubility of amines. Not only can a primary or a secondary amine form hydrogen bonds with molecules that are identical to itself, they can also form hydrogen bonds with water, and that's what's shown over here. Okay, you can see all the delta pluses and the delta minuses on the amine are shown here. And then what do we have? We have a hydrogen bond from the delta plus of a hydrogen with the delta minus of the oxygen on a hydrogen. Similarly, we see another hydrogen bond between the delta plus on the hydrogen of the water and the delta minus of the nitrogen on an amine. So again, this is one of those things where we expect you to be able to explain hydrogen bonding thoroughly to other students and to understand hydrogen bonding in this class. Okay, it's one of the key things is that you have to understand intermolecular forces when you leave chemistry 102. In fact, you should understand it after the first few weeks. We talk about it so much. Another kind of rule of thumb, students like rules of thumb, is that amines that are up to 6 carbons long are generally speaking going to be water soluble, and that's due to their ability to form hydrogen bonds with the water. Well, what's going to happen is that you're going to see the solubility in water of an amine is going to decrease, obviously, as the length of the hydrocarbon portion of the molecule increases. Now, why would that be? Because hydrocarbons are nonpolar, right? As that nonpolar chain gets bigger and bigger and bigger, it's going to render the molecule less and less soluble in water. And so again, this is just a general kind of rule of thumb that if we have an amine up to 6 carbons long, it's generally speaking going to be water soluble. All right, there we go. Well, here's what you came for, nomenclature, right? All students love nomenclature. And I promise to you that if you understood the nomenclature of alcohols, things like alcohols and alkenes, then the nomenclature of amines isn't that much of a stretch. There's just one, kind of added layer of complexity when we deal with secondary and tertiary amines, but I'll go over that. So that's why we start with just talking about primary amines, okay? Because when we have secondary and tertiary amines, it gets a little more complex, okay? And again, that's coming up on another slide. So again, all we're talking about here is primary amines like RNH2. Okay, so we're going to have 2 nitrogen-hydrogen bonds in our primary amine. The first thing we're going to do is we're going to find the parent compound. That's the longest continuous carbon chain that contains the amine group. Then we're going to drop the E of the parent name and add the suffix amine. So that means methane, for example. Methane, you would drop the E and that would become methane amine. Okay? Give me another one. If you had, I don't know, octane, you drop the E and that would become octane amine, like that. Sometimes people will pronounce it octanamine or methanamine. I could just call it octanamine, methanamine, ethanamine, propanamine, butanamine, so on and so forth. Next, you're going to number the parent chain to give the amine carbon the lowest possible number. And so the carbon that has the amine directly attached to it on your primary amine, that is always assumed to be carbon number 1. For example, this would be carbon 1. This would be carbon 1. Yeah, this would be carbon. No, actually, it's not in this one. But anyhow, I digress. And then you name and number all the substituents as usual. Do I have the names on here? Yeah, I do. Okay, so here we find the longest carbon chain in the first example. It's got 1 carbon, so that's a methane derivative. We cross out the E and we call it methanamine. If we have propane, we drop the E, we get propanamine, and we have the amino group on carbon number 1. And in the second one, again, we find the longest carbon chain, and we want to give that amine carbon, we want to give it the lowest number possible. Okay, so we would number this way: 1, 2, 3, 4, 5, like that, and this becomes 2-pentanamine, 2-pentanamine, just like that. Now again, naming primary amines is the simplest type of amine nomenclature, but we're going to look at secondary and tertiary amines, and this is where it gets a little bit more interesting. The prefix N-alkyl is added to the name of the parent for secondary and tertiary amines. So how did they come up with these two names for these molecules that are shown at the bottom? I'm just going to highlight one thing because you guys always have good questions. Is that this N, when it's printed in a book, for example, it's usually italicized. Okay, it's almost always italicized. You see how they're italicized here, these N's? Well, let me explain how to use those. Okay, in this molecule here on the left, where did they come up with this name? N-methyl ethanamine. Well, let me show you. The first thing the person did is they identified the longest carbon chain. It's got 2 carbons, right? Carbon 1 and carbon 2. Why did I call this carbon carbon 1? Because we want to give the nitrogen, the carbon with the nitrogen on it, the lowest possible number. Now, if this was CH3, CH2, CH3 with NH2 on it, right? That would simply be ethanamine. Ethanamine. But now we've spiced things up, right? We've put a methyl group on here. And so since that methyl group is attached to the nitrogen, we call it N, and that's where this italicized N comes from. We call it N-methyl, right? Because this is a methyl, so N-methyl ethanamine. We just give the rest of the name of the molecule. Similarly, for this example here, if we simply had CH3, NH2 like this, this would be methanamine. Nothing new there. But if I have 2 methyl groups, then they're both attached to the nitrogen. We call it NN. So you put an italicized N for every group, and then it would be dimethyl. So this is NN dimethyl methanamine, like that. Now again, these are IUPAC names. We're going to look at common names in a second, because if you worked in a lab, Johnny, with another chemist and you said, pass me the NN dimethyl methanamine, I mean, they would be able to figure out what it was, but they'd be like, what? What is that? So Greg says that he's seen lowercase n's in the future, or in the past, sorry. Maybe he's seen them in the future too. I don't know. Maybe he's practicing his time travel. But anyhow, other n's that you see in nomenclature in organic chemistry, if you see something like N-propanol or something like that, N-propanol, that's lowercase n. That actually stands for the word normal. Okay, so that means it's on the first, the hydroxyl's on the first carbon, so it just means normal. Anyhow, our book doesn't use that a whole lot, I don't think. Anyway, there you go. And we're going to look at some more examples. But before we do that, I want to talk about naming aromatic amines. Several aromatic amines have special IUPAC approved names. The good news is that you already know one of them, right? You already know aniline. We've seen that molecule enough. If every once in a while I have a student that says, Mr. Dean, I Googled this compound and you told me how to name on Wikipedia, and it had like 16 names or something crazy. I mean, I'm exaggerating, but if you were to call it benzenamine, it technically is not an incorrect name. I wouldn't say it's widely used. Again, in fact, right, if you were to ask somebody in the lab, pass me the benzene amine, they'd be like, what? You mean the aniline? Yeah, okay. They would kind of look at you weird. Again, not that there's anything wrong with those names, they're just not commonly used, right? If you look up the IUPAC name for sucrose, which is sugar, table sugar, if you were to say to somebody, pass me that, and you gave them the IUPAC name, they'd be like, huh? Okay, so anyhow, amines of benzene are named as aniline derivatives. The systematic name is benzenamine, or the IUPAC name. As additional groups are attached, they are named as N-substituted derivatives of aniline. Let me give you an example because I don't have an example on this slide of this bullet point here. I'll put it up here. So let's say you had an aniline derivative and you put a methyl group on the nitrogen of aniline. You would call that N-methyl aniline. That, okay? Let's say you had, and I'm just coming up with examples off the top of my head here. Let's say you had aniline and you put two methyl groups on the nitrogen, right? Instead of two hydrogens, you'd call that N dimethyl, N dimethyl aniline. There we go. All right. I think I might have mentioned the toluidines earlier. Maybe it was the xylenes. But anyhow, if you have an amine and it only has one methyl group on it, that's what we call a toluidine derivative. Of course, if the substituents are in a 1-3 arrangement, we call it meta-toluidine. If they're, son of a gun, I can't make the number 3. If we have them in a 1-2 arrangement, that's called orthotoluidine. And if they're in a 1-4 arrangement like this, we call that a paratoluidine. So the toluidines and anilines, make sure you know those. Okay, now that we've covered IUPAC names, let us take a look at common names just for a second here. It says here that for common names, we're going to name the alkyl groups attached to the nitrogen in alphabetical order. Then we're going to throw the word amine on the end. You can already see how it's a lot simpler. Okay, the name is continuous. We have no spaces. Look at these examples. You're gonna love this. Okay, if I have a methyl group on my amine, I call it methylamine. If I have 2 methyl groups, I call it dimethylamine. If I have 3 methyl groups, I call it trimethylamine. If I have an ethyl group, I'd call it ethylamine. If I had an ethyl and a methyl, I'd call it ethylmethylamine. Why do I put them in that order? Because I'm doing it in alphabetical order, and E comes before the letter M. Nothing more to it than that. So you can see why common names of small amines are much more intuitive. And so they kind of roll off the tongue a little bit faster. These are some medically important amines. We'll take a quick look at these. You've probably all heard of crystal meth before, which is methamphetamine, which is shown here. So it says here that amphetamines can stimulate the central nervous system. Whenever a seasoned chemist anyway, sees this molecule right here, right away they recognize this as amphetamine. And then if we add a methyl group onto the nitrogen, right here, that is methamphetamine. Okay, and you probably all heard about crystal meth and things like that. Also, analgesics, which are pain relievers, and anesthetics, which are pain blockers, often have amines in them. Things like Novocaine. If you've ever been to the dentist, you may have been given Novocaine in the past, or Demerol. Okay, and you can see how we have amines here. You can see that Novocaine is an aniline derivative, and the Demerol is like a 6-membered ring that's not aromatic. It's got a nitrogen in it. Okay, I'll just show you. If you have a cyclic amine like this has got a name. It's called piperidine. Piperidine. Anyhow, I don't think you have to have that memorized in this class, but piperidine. What else? Decongestants. So you've probably all heard of ephedrine and pseudoephedrine. Well, ephedrine used to be marketed in things like, I forget all of the drugs, but things like Contact C was a cold medication that you used to be able to buy over the counter. But the problem with that is that people were buying the cold medication and they were reducing off this hydroxyl here. And when you do that, you end up with methamphetamine. So it was a quick way to take cold medicine or cold medication and convert it into meth or methamphetamine. And so pharmaceutical companies tried to find ways to do an end run around people who want to do bad things to themselves. And so they developed an enantiomer, or sorry, a diastereomer rather, of ephedrine. You see it have these two stereocenters here. Where's my, here we go. We have a stereocenter here and a stereocenter here. This one is the same in pseudoephedrine, but you'll see that this one is reversed. Okay, you can see how the amino group here is going behind the page or behind the board or behind the screen, and here it's coming out. And so even if you remove the hydroxyl of pseudoephedrine, you don't get crystal meth, okay, because the orientation of this methyl group, of this N-methyl group rather, counts. And anyhow. And then we have phenylephrine, which is another derivative to try to stop people from making methamphetamine. Sulfa drugs, there's not a whole lot that I can tell you about sulfa drugs, except they were used a lot in a long time ago, like in the Second World War. These were kind of like the first antibacterials, the first antibiotics developed, and they've since kind of gone out of vogue, but they did save a lot of lives a number of years ago. Okay, reactions involving amines. Just give me 1 second here to grab a drink of water. Oops. All right, who would like to take a break and try some practice problems where we take a look at some nomenclature? Anybody? I know I would. So why don't we give a couple of compounds the old college try here. And for these examples, what I want you to do is I want you to give me both the IUPAC and the common name. So we want IUPAC, and common names for these molecules. So I'm just going to give you a couple of molecules here. Let me see here. If we do this, so we'll start with this molecule, like this. Okay, it's kind of an ugly bond. Didn't fix it, did I? Yeah. What's another one we could try? Is this, and then try this one over here, maybe. Oops. All right, does anybody have a name for the first compound? Okay. Yeah, we get some ideas here. All right, well, let's take a look at it as a group. The first thing we're going to do is we're going to find the longest carbon chain. So when we're doing the IUPAC name, we'll find the longest carbon chain, which is 1, 2, 3, 4 carbons. So that would be butane, right? If you had a 4-carbon hydrocarbon. And so if we have the amino group at the second carbon, this would become 2-butane amine, like that. If we want to give it a common name, then all we have to do is name this alkyl group. Could anybody name that alkyl group? It's not a methyl, it's not an ethyl. Because you only use the capital letter N, italicized N, for secondary amines. Okay, that's only used for secondary or tertiary amines. This is a primary amine, so we don't have to use any of those prefixes. All right, can anybody tell me what this alkyl group is? It might be a kind of a dark horse, one that we don't talk about a lot, but this is a butyl, right? It's not a butyl. It's not an isobutyl. It's not a tert-butyl. It's a sec-butyl. So this would also be called, the common name would be sec-butyl amine, like that, sec-butyl amine. Okay, let's take a look at the next one. We can start with maybe the common name. Could anybody tell me what this alkyl group is called? Anybody give me the name of that alkyl group? It's also got, yeah, there we go. It's got 4 carbons, so this would be you could call it T-butyl amine. That would work. Or you could call it tert-butyl amine. Either one is perfectly fine. Perfectly fine. And if we want to give it an IUPAC name, the first thing we're going to do is we're going to find the longest carbon chain. And the longest carbon chain in this molecule has 1, 2, 3 carbons in it, like that. So we have our methyl group on carbon 2, and then we have our amine on carbon 2 of a 3-carbon chain. So this would be 2-methyl, right? Because we get a methyl group over here. So this is 2-methyl, 2-propanamine. Propanamine. Like that. Okay, so that's the IUPAC name. I'll do this last one for you because it's kind of a little bit of a long one. Let's start with common. I think that's easier. We've got an isopropyl group here, we've got an ethyl group here, and we've got a methyl group there. Let's put them in alphabetical order. And so this would be ethyl, isopropyl, methyl, amine, like that. And then our IUPAC name, again, we find the longest carbon chain, which is going to be the longest carbon chain, which would be 1, 2, 3 carbons like this. Remember, this is a tertiary amine, and so we have an N. On this side, we have an N-methyl, and over here we have an N-ethyl. Okay, but those 1, 2, 3 carbons, that is the longest straight carbon chain in the molecule. That's unbroken. And so this would be a 2-propanamine, right? Some kind of 2-propanamine derivative. E comes before M in the alphabet. And so when we put all of this together, first I'll delete some of these circles that I have here. There we go. Make it a little prettier. We have N-ethyl. So N-ethyl, N-methyl, 2-propanamine. All right, so remember, the only time we use those N prefixes are when we have a secondary amine or a tertiary amine. Okay, we're dealing with primary amines. We don't have to worry about those prefixes whatsoever. They don't even come up in the conversation. All right, well, let's get back to where we were. Find my slides. Okay, and let's talk about reactions that involve amines. So now we're switching gears entirely, and we're going to be talking about all kinds of interesting chemistry that deals with amines. The prefixes, things like tert, sec, iso, that is going to be in chapter 10. All right, so how would we prepare an amine? Well, the first thing that is shown here is that we can prepare an amine by the reduction of an amide or a nitro compound. And those are both exemplified on this slide. The first one shows the reduction of an amide. And if we take that amide and we treat it with reducing conditions, remember that when we have a hydrogen atom shown inside square brackets. This is just another way of saying reduction or a reducing agent. Okay, it doesn't specify what it is because there are so many out there probably that could do this reaction. But anyhow, what you need to know is that we end up losing, we lose oxygen, and we end up gaining hydrogens, right? And that is the definition of reduction in organic chemistry. Loss of oxygen or gain of hydrogen or both simultaneously, right? Okay, so there's a reduction of an amide. Of course, the R2 groups here, they could either be hydrogen atoms or they could be alkyl groups. Aromatic amines are prepared by the reduction of nitro compounds. The same thing that I said that was deleted is that, again, when we see the H in brackets, that means the same thing as reduction. Reduction. And you can see here that we're losing. We're going to lose those two oxygens, right? And we're gaining hydrogens. And so, therefore, it is apparent that we're reducing that nitro to an amine. So we can take nitrobenzene and convert it into aniline by reduction. So again, you've got to be familiar with these two reactions, which are both reductions, the reduction of an amide or the reduction of a nitro to produce an amine. Amines are also bases. We spoke about this at the very beginning of the lecture today. I said that amines are weak bases, but they are bases nonetheless. What's the definition of a base? Well, if you remember the Bronsted definition of an acid, Bronsted said an acid is something that donates H plus in solution. And he also said that a base is something that accepts H plus in solution. So bases are proton acceptors. They accept protons when dissolved in water. And the way that they do that, the actual mechanics behind it, is that the lone pair of electrons on the nitrogen can be shared with a proton from the water. And the way that we represent that, not in our textbook, but in higher level textbooks, is they'll actually use a curved arrow. And they'll start on a pair of electrons, and they'll show that pair of electrons with an arrow pointing from the lone pair to the hydrogen. And what that means is that this is a bond being formed. Bond being formed. And that is this bond right here. That's the new bond that's formed between nitrogen and this hydrogen. Okay, well, what else is going to happen? Well, not only are we going to form a bond, we're also going to break a bond, right? We're going to simultaneously break this bond. The oxygen already has two bonds and two lone pairs, okay? And then this second curved arrow represents a bond. I'm going to try to be consistent here. A bond breaking. Okay, so we form a bond and we break a bond simultaneously. And now the hydroxide. Okay, so the amine is the base. Why? Because it accepts H plus. And then we end up with what's called an alkyl ammonium ion. Now, hopefully you remember from general chemistry, right, the difference between NH3, which is ammonia, and if we have NH4 plus, that's ammonium. Okay, it's a polyatomic ion that you should have memorized in general chemistry. So if we replace one of the hydrogens in ammonium, and I can draw the Lewis structure of ammonium, the ammonium ion right here. Okay, again, this is ammonium. If we replace one of those hydrogens with an R group, and that R group is an alkyl group, then we call it an alkyl ammonium ion. Okay, now again, the reason that amines are basic is because when you put them in water, they produce hydroxide, and hydroxide is a base. All right, so amines as bases. Here's an example. It's a simple example, but a good one nonetheless, of an amine and how it would behave in water. We take methylamine, which has a very fishy odor. Okay, it smells like rotten fish. If you take methylamine and you put it in water, again, I'll show you the curved arrows. The lone pair on that nitrogen is actually going to grab that hydrogen, and these electrons in this bond between the oxygen and the hydrogen are going to break, and they're going to go on to the oxygen to form the hydroxide ion. Okay, Now, something else I should point out here is that we have an equilibrium arrow. Remember, if we have an arrow going in one direction, that's a complete reaction, right? Complete reaction. Whereas if we have these arrows, this represents equilibrium. Okay. Now you notice that the two arrows are the same length, so it doesn't indicate which side the equilibrium lies to, but I can tell you that amines are pretty weak bases. Okay. It's actually going to lie more to this side. Okay. But again, all you really need to know is that it's an equilibrium. All right, give me a thumbs up if you follow me on that. An amine behaves as a base. The lone pair on the nitrogen can accept a proton from water, make hydroxide, because we're going to look more at amines behaving as bases. Good. All right. Well, I told you that we'd also look at amines acting as bases. And now we're going to look at an amine acting as a base in a neutralization reaction. All right, remember that we told you back in Chemistry 101, you probably learned things like this. I'll give you an example. If we have HCl, hydrochloric acid, which is a strong acid, and we react it with sodium hydroxide, which is a strong base, so this is an acid, and this is a base, what do we end up with? We end up with a salt, and the salt in this case would be sodium chloride, which just happens to be table salt. And we also end up with water, right? And you'll see the same thing here. An amine is a base. Okay, we don't end up with water in this case, but if we take an amine, we end up with a salt. Okay, we don't end up with water, but we do end up with a salt. You're like, well, this doesn't look like table salt to me. Well, a salt is the combination of a cation and an anion. And the alkyl ammonium is a polyatomic ion. It's a cation. Okay? So again, if we were to show the Lewis structure of the HCl, okay, here's the Lewis structure of HCl, like that. Here's the curved arrow of what's happening. This nitrogen is going to take that hydrogen atom, and this bond is going to break. Okay, so we end up with chlorine converted into chloride, like that, and we end up with our alkyl ammonium salt. Again, we have an anion, chloride, and we have a cation, the alkyl ammonium. It's not a salt like potassium bromide. It's not a metal and a non-metal. It's all non-metals, okay? It's a special case, but it's still considered a salt because it's made of two ions, a cation and an anion. All right, nitrogen can form four bonds, absolutely, but it will have a positive charge. Okay, if you remember how to calculate formal charge from general chemistry, if we look at this nitrogen, right, formal charge is equal to the number of valence electrons, subtract the number of sticks, not strix, the number of sticks. Great, I don't know what's up with my Apple Pencil. And the number of dots, right? Dots are the same thing as unpaired electrons. Well, for this nitrogen atom, okay, for this nitrogen has 5 valence electrons. It's got 4 sticks, right? 4 bonds. We call those sticks. Okay, so and it's got 0 lone pairs. So 5 minus 4 minus 0 gives us +1, and that's why the nitrogen has a +1 charge. Okay. Now, how would we go about naming an alkyl ammonium salt? We just saw an alkyl ammonium salt here. Well, let's figure out how we might name one, because alkyl ammonium salts are actually pretty important, and we'll talk about why in a little bit. The first thing you do is you name the amine salts by replacing the suffix amine with ammonium. So if we had methylamine, it becomes methylammonium, right? We see that down here. Methylamine becomes methylammonium. If you had ethylamine, it would be ethylammonium, propylammonium, so on and so forth. Okay, so we would replace amine with ammonium. We get that. We add the name of the anion. If your anion is chloride, it's whatever chloride. If it was bromide, it would be bromide. If it's iodide, it's iodide, so on and so forth. So nothing more than that. All right. Now what it says here is that converting amines like methylamine, which I told you has a very fishy odor, methylamine or methanamine. Methylamine is the common name, right? It says here that if you take those amines and you convert them to salts, it makes insoluble amines soluble in water as the salts are ionic, right? You guys remember that ions dissolve in water, right? An amine, not necessarily, I mean, methylamine is a very small amine, so it probably is soluble in water, right? Because we set up the 6 carbons to be water soluble. But when you get into bigger amines that are not going to be water soluble, if you convert them into a salt, right, they will become water soluble. Why? Because salts made up of cations and anions are ionic, and they're going to interact with the water molecules, and it will solubilize them. What would happen if we took an alkyl ammonium salt and we reacted it with a base? You know, before I get into that, let me just mention one more thing about this, because I told you that methylamine has, you know, kind of a stinky fish odor. Well, what do you do when you get a piece of fish at a restaurant? A lot of times, maybe not all the time, depends on where you eat, but a lot of the time they serve fish with lemon. There's a reason, historical reason as to why they serve lemon wedges with fish. It's because of the citric acid that is found in lemon. Historically, oftentimes when people ate fish, it wasn't always necessarily fresh. Back before refrigeration was abundant, like it is nowadays, or it has been for the past few decades. But before that, oftentimes people ate food that was rotting or getting close to rotting. And so what they would do to alleviate the fish odor is that they would add lemon juice to it. And what happens is you have something here that's going to have a really low boiling point, and your nose can detect it. But when you convert it into a salt, okay, with the citric acid, you end up with something that has a very high boiling point, and so you don't detect it with your nose, right? Now, what about those alkyl ammonium salts and what we can do with those when they're in a base? Well, I'll just tell you right now that an alkyl ammonium salt is an acid. Okay? It's a weak acid, but it is an acid. We could put here weak acids. Okay, alkyl ammonium salts are weak acids. Well, alkyl ammonium salts, if they're acids, they can react with a base. Okay? A hydroxide ion is OH minus, right? And that's a base. So of course the acid can react with a base, but in this case, we end up forming water, right? An acid, the alkyl ammonium, which is an acid, it's a weak acid, but it's still an acid plus a base. Okay. We don't end up with a salt in water, but we do end up with water in this case, and the free amine. How does this happen? Well, what's a base? Like hydroxide ion, bases are H plus acceptors. And so the hydroxide is actually going to grab the proton from the alkyl ammonium, and this pair of electrons is going to go back onto the nitrogen to form the new lone pair, like that. Okay? It says here that the reversal of the alkyl ammonium salt to the amine is extremely important in many drugs. That brings us to our next topic, which are quaternary ammonium salts, and there are several different quaternary ammonium salts that are found in disinfectants, for example. Quaternary ammonium salts are ammonium salts. They have 4 organic groups bonded to the nitrogen. Quaternary ammonium salts, they have very long carbon chains. They're sometimes called quats. So when we have a big long chain, we call those quats. And they have a general formula like this, where we have a nitrogen with 4 R groups, and then we have our halide ion, most commonly chloride, to make up our salt. Here's an example. Choline is a very important quaternary ammonium salt. We'll look at the structure of choline more later on in this lab when we talk about lipids, like phospholipids. But let's move on from here and take a look at some other examples of quaternary ammonium salts. Benzalkonium chloride and cetylpyridinium chloride, sorry. These again are 2 examples of quaternary ammonium salts. For example, this one here, cetylpyridinium chloride, is found in the mouthwash Scope. And so you can see that these are important examples that serve as disinfectants and antiseptics. They're also found in things like those what are they called? What are the wipes? The Clorox wipes that you buy at Costco. You know, these are pretty hot item a few months ago when when the pandemic first hit. Everybody was trying to buy up these things, and that's what's found in them, is these quaternary ammonium salts that are good disinfectants. All right, well, that brings us to section 15.2, which deals with heterocycles.